Hey guys, for calculus, this is from 3.7, and for pre-cal, when we start to learn calculus at the end of the year, this is from 4.7. This lesson is called optimization. This section is going to be a lot of writing, bear with me, but it is the application of extremas. Like, why do we learn to find the max and min of things? Is it just to find the lowest point on a graph? So you're going to see how this comes in handy, and for any of you who are considering some sort of like a business major or things like that, this is something you're going to see a lot in the future. So we want to be able to optimize profit, right, and minimize expenses when we're in a business. So, for example, if you work for a zoo and you need to buy fencing, you want to figure out how you can have the maximum amount of area for the animals to have space, but yet the minimum amount of fencing so that you can save money. So you want to strategize like that. And there's people whose jobs are literally to come up with this information. So let's check this out. The steps that we're going to do is we're going to identify the givens and what they are asking you to solve for. If possible, make a sketch. Okay? Then they're going to give us two different equations that they're going to want you to work with. Okay? One of them we're going to call the primary equation, and the other one we're going to call the secondary equation. So the primary equation is the one that they want you to maximize or minimize. So for example, if I said we want a maximized area with a certain amount of fencing, then your primary equation would be the area formula. Okay? Step 3 would be to use the secondary equation, the second equation that they give you, to rewrite the primary equation so that you have it in terms of one variable. So for example, if you got stuck with an area formula, base times height, you'd be working with implicit differentiation because there's two variables, where if you can change it using the secondary equation to only have one variable, now you can do something as simple as power rule or product rule. All right. So step 4, you're going to determine a domain that makes sense with a scenario. For example, when you're talking about how much fencing you can use, you're most likely never going to use a negative number as your answer. You can't have a negative amount of fencing. Once you've created that single rewritten primary equation with one variable, you're going to use the first derivative test to solve for that max or min. Okay? So we're going to walk through 3 full examples today. Let's check out the first one. It reads, a manufacturer wants to design an open box having a square base and a surface area of 108 inches squared. What dimensions will produce a box with a maximum volume? So you can already see here that what they want you to maximize is the volume, okay? And then the second equation that they gave you is the dimensions of the box, so you can know what the surface area is. And they went ahead and told you what the surface area would look like for this open box. So I can say that my primary equation so for volume, for 3-dimensional, we have length times width times height. Now, they tell us that this open box has a square base. So, I mean, the height could be a different dimension, but the base, the length and the width are the exact same. So I'm going to call them both x for argument's sake. So I can say that this is x because they're going to be the same measurement, and this is height. So we can also say that volume is going to be x squared times h. So I'm already down to 2 variables. Now, the surface area formula, which is the secondary, I'm just going to rewrite what they gave us. Now, they also told me over here that the surface area is 108. So I already know what this equation is going to equal. So if we give a quick sketch, and bear with my drawing here, we have a square base, okay? And then the height could be something different. Okay? So now, again, we know this one's primary because they want us to find the maximum amount of volume, which means I'm going to try and rewrite this secondary equation to isolate either H or X so that I can plug it in here, and now I can have volume in terms of one variable. Okay? So the question is, do you want to isolate the H or the X? Honestly, either way that you do it, it will work out the same. So I'm going to go ahead and isolate H just because it's in one term instead of stuck in both of them. So I can subtract this x squared, and now I'll say 4xh equals a negative x squared plus 108. And then divide this by 4x. So h equals, remember each term gets divided, so I'd say negative x squared divided by 4x plus 108 divided by 4x. All right, so here I would continue to just clean h so that it's not as messy. I'm going to say negative 1/4 and then an x squared divided by x. And then plus 108 divided by 4 gives me 27. And if I were to be doing this, it would be easier to use the x brought up with a negative exponent for power rule. But remember, the whole purpose of me isolating this h now is to plug it up into here so that, remember, my primary function, which is the one I need to do the max, the first derivative to, will be in terms of one variable. So I'm going to rewrite my primary. And now I'm going to say volume equals x squared times, and instead of writing h, I can put what I isolated h to equal over here. So times negative 1/4 x plus 27 x to the negative first. I could do product rule here, or I could distribute this so that I only have to do power rule. Okay? So if I distribute this, I have negative 1/4 x cubed plus 27, and then x squared and x to the negative first just give me x to the first power. Okay? So now that I have my primary equation rewritten, again, they want us to find the maximum volume. Here is where I'm going to do the derivative. I'm going to do the derivative of volume with one variable. Now it should be easy. V prime. All right, so here's where the first derivative test comes in. I'm going to have negative 3/4 x squared plus 27. Okay? I'm going to set this equal to 0. Move the 27 over. This negative 3/4 is currently being multiplied. So in order to move it to the other side, I need to divide it. Okay, I'm going to come up here just so I have some more room. So remember, when I divide fractions, I keep change flip. Right now I have x squared equals negative 27/1, and then I'm going to multiply by the reciprocal. Okay, I personally like to reduce my fractions before instead of after. So for example, I know 3 goes into 3 one time, and 3 goes into 27 9 times. So what I'm really working with is 2 negatives make a positive, and then 9 times 4 is 36. So I have x squared equals 36, and the square root of that gives me plus or minus 6. So we had said that step 4 was to determine the domain. If I'm talking about dimensions of a box, I can't really have a negative dimension, so the only one I'm going to be working with is x equals 6. So far I found one of the dimensions. I found what the x, technically I found 2 of them. I found what the x was. Okay? So now all I have to do is, in order to say my dimensions, like length times width times height, blank by blank by blank, I have the x's. Now all I have to do is solve for h. So I can say, okay, if h equals negative 1/4 x plus 27 x to the negative first. I'm just going to plug in that 6. Remember that that x to the negative first brings it down. So you can either clean this up by hand. So now that we have our height and we have our x, which is our base and our width, right? So our length and our width, excuse me, from our base. Now we can say that the dimensions which was length times width times height, right? Which we then replaced x for length and width because they were the same. Now we can say that the dimensions are going to be a 6 by 6, and my height was 3 by 3, and the unit of measurement here was inches. Okay. So those would be the dimensions that would produce a box with a maximum volume.